Hello and welcome to Boring History for Sleep. Tonight, we will be exploring a subject of quiet, unassuming presence in our daily lives. Consider the common wood-cased pencil, an object of such simple utility that it often escapes our notice. At its tip, a point of graphite and clay. At its crown, a small, resilient nub, usually pink, held fast by a thin metal band. We see it, we use it, but we rarely consider the century of focused industrial chemistry and mechanical engineering that resides within that tiny eraser and its metallic collar. This unassuming component is not a single, static invention, but the product of a slow, deliberate evolution. To truly understand the quiet history of this humble tool of correction, we must examine its origins and trace the subtle, almost imperceptible shifts in its material heart and mechanical soul. Our story begins not with the eraser as we know it, but with the problem it was born to solve: the semi-permanent nature of a graphite mark. Before the late 18th century, the most common method for correcting a graphite or charcoal inscription was to use a crust of stale bread. The soft, slightly moist, and mildly abrasive crumb of the bread could lift the dark particles from the paper's surface, a technique that was effective enough for its time, but one that came with obvious drawbacks of perishability and mess. The first significant step away from the bakery and toward the laboratory came with the introduction of natural rubber to Europe. Known by its Quechua name, caoutchouc, or weeping wood, the milky latex sap of certain South American trees had been known to indigenous peoples for centuries, but its properties were a curiosity to European naturalists. In 1770, the English engineer Edward Nairn is credited with being the first to commercially market rubber as an erasing agent, selling small cubes of the substance as erasers. In the same year, the famed scientist and theologian Joseph Priestley noted in a preface to one of his works, "I have seen a substance excellently adapted to the purpose of wiping from paper the mark of black-lead pencil." He described it as a gum from the East Indies, sold in cubical pieces of about a half-inch, which cleanse a line of black lead, and is much more effectual than bread. This raw, untreated rubber was a remarkable improvement, but it was far from perfect. It was sticky, especially in warm weather, would foul with graphite particles quickly, and most critically, it would putrefy and rot over time, emitting a foul odor. The material was an organic substance, and like the bread it replaced, it was subject to decay. The great leap forward, the event that made the modern rubber eraser possible, was the discovery of vulcanization by Charles Goodyear in 1839. Goodyear, a relentless and almost obsessive inventor, had spent years trying to stabilize natural rubber. Through a now famous accident involving a hot stove, he discovered that heating rubber mixed with sulfur transformed the material entirely. The sticky, pliable gum became a strong, elastic, and durable substance, resistant to heat, cold, and decay. The process, which he named after Vulcan, the Roman god of fire, created crosslinks between the long polymer chains of the rubber, known as polyisoprene. These sulfuric bridges gave the rubber its memory, allowing it to return to its original shape after being stretched or compressed, and it dramatically increased its durability. Goodyear's discovery was transformative for countless industries, but its application to erasers unlocked the potential for a truly reliable and lasting tool. However, the pencil and the eraser remained two separate objects. One would write with the pencil and reach for a separate block of vulcanized rubber to make corrections. The conceptual union of these two tools was patented in the United States on March 30, 1858, by a stationer from Philadelphia named Hyman Lipman. His patent, number 19,783, was not for an eraser itself, but for a lead pencil and eraser. The patent described a pencil in which the traditional graphite core was only inserted partway down the wooden shaft. The remaining hollow portion at the top was designed to contain a separate piece of India rubber, gutta percha, or other erasing substance, which was secured by the wood of the pencil casing itself. Lipman's idea was ingenious, a simple and elegant combination of two complementary functions into a single instrument. He eventually sold his patent to the stationer Joseph Reckendorfer for the then staggering sum of $100,000. Despite the brilliance of Lipman's concept, its initial execution was somewhat crude. The eraser was essentially glued or wedged into the end of the pencil's wooden body. This method lacked durability, and the eraser could become loose. The true innovation that would create the iconic pencil we know today was the development of the ferrule. A ferrule, in its broadest sense, is a ring or cap, typically made of metal, used to strengthen the end of a handle, stick, or tube, and prevent it from splitting or wearing. Its application to the pencil was a simple, yet revolutionary piece of mechanical design. It provided a dedicated, durable housing for the eraser plug and a secure method for attaching it to the wooden pencil barrel. This brings us to our starting point of 1870. By this time, the American pencil industry was beginning to coalesce into a manufacturing powerhouse. Companies like Eberhard Faber, which had established its first factory in New York City in 1861, and the Joseph Dixon Crucible Company of New Jersey, were scaling up production and refining their methods. The Gilded Age was a period of immense industrialization, and the demand for writing instruments grew exponentially with the expansion of commerce, education, and bureaucracy. The pencil with an attached eraser was no longer a novelty, it was becoming a standard. Let us first examine the eraser material itself during this period. From 1870 to the turn of the 20th century, the core ingredient was, without question, vulcanized natural rubber. The rubber was sourced primarily from the Amazon basin in Brazil, harvested as latex from the Hevea brasiliensis tree. This raw latex was then coagulated, often by smoking it over a fire, to form large, rough balls of raw rubber, which were shipped to factories in North America and Europe. In the eraser factory, this raw rubber was not used in its pure form. Pure vulcanized rubber would be too soft and gummy, smearing graphite rather than removing it. The key to an effective eraser was a carefully balanced recipe, a compound of several ingredients mixed together before the vulcanization process. The most critical additive was an abrasive. The prevailing theory of erasing at the time was one of physical abrasion. The eraser worked by gently scraping away the topmost fibers of the paper, taking the embedded graphite particles with them. The perfect abrasive had to be hard enough to dislodge the graphite, but not so hard that it would tear or scuff the paper. The abrasive of choice was pumice. Pumice is a type of volcanic glass formed when superheated, highly pressurized rock is violently ejected from a volcano. The rapid cooling and depressurization creates a foam-like structure with countless tiny air bubbles. This results in a very lightweight and abrasive material. It was typically mined, crushed, and then finely milled into a consistent powder, often referred to as pumice flour. The fineness of the grind was critical. Too coarse, and the eraser would be harsh and damaging to the paper. The best pumice was sourced from the volcanic islands of Italy, such as the Lipari Islands, and was shipped in large quantities to American factories. The typical eraser compound of the late 19th century would therefore begin with a base of natural rubber. To this, workers would add a precise measure of finely ground pumice. The next essential ingredient was the vulcanizing agent itself, sulfur. Added as a fine yellow powder, the sulfur was the chemical key that would later, under heat and pressure, forge the crosslinks between the rubber polymers. Another category of additives was fillers or extenders. These were largely inert materials added to the compound to increase its bulk and reduce the overall cost. High-quality natural rubber was expensive, and fillers allowed manufacturers to produce erasers more economically. Common fillers included whiting, which is finely ground calcium carbonate, and barytes, a dense mineral composed of barium sulfate. These materials did not significantly contribute to the erasing quality, but they added body and weight to the finished product. Finally, there was the matter of color. The iconic pink or reddish hue of the common pencil eraser was not an inherent property of its functional ingredients. Natural rubber compounds were typically a dull gray or brownish color, and manufacturers added colorants for branding and aesthetic purposes. The most common pigment was iron oxide, also known as hematite or, more simply, rust. This inorganic pigment was cheap, stable, and produced a consistent reddish-pink color that became synonymous with the pink pearl eraser, first produced by Eberhard Faber in this era. The color served a secondary purpose of masking any visual imperfections or discolorations from the other ingredients in the compound. The manufacturing process for these eraser plugs was a feat of industrial chemistry. The raw rubber was first placed into a machine called a masticator, which used powerful, heated rollers to shred and soften the rubber, breaking down its natural structure and making it more receptive to the other ingredients. Then, in large mixing mills, which resembled giant two-roller dough mixers, the masticated rubber was blended with the pre-weighed quantities of pumice, sulfur, fillers, and iron oxide. The operators of these mills had to be skilled, folding and passing the thick, heavy sheet of rubber compound through the rollers repeatedly until a completely homogeneous putty-like mass was achieved. This colored, unvulcanized rubber compound was then fed into an extruder. This machine worked like a giant meat grinder, with a screw mechanism forcing the rubber compound through a die of a specific shape and size, typically a round or hexagonal profile, matching the shape of the pencil it would eventually adorn. This process formed long, continuous cords of eraser material. These cords were then cut into small plugs of the precise length required for the eraser tip. These small, soft plugs were then ready for vulcanization. They were arranged on large trays, dusted with soapstone or talc to prevent sticking, and loaded into massive, heated ovens or autoclaves. Here, under controlled temperature and pressure, the sulfur would react with the polyisoprene chains of the rubber, cross-linking them and transforming the soft, pliable plugs into the firm, elastic erasers we would recognize today. This curing process had to be carefully monitored. Too little heat or time, and the eraser would be undercured and gummy. Too much, and it would become overcured, hard and brittle. After curing, the plugs were tumbled in large drums to remove any excess dusting powder and to smooth their edges before being sent for assembly. While this chemical evolution was taking place within the eraser itself, a parallel mechanical evolution was occurring with the ferrule. As we established, the ferrule was the metal band that held the eraser to the pencil. In the 1870s and 1880s, the material of choice for high-quality ferrules was brass, an alloy of copper and zinc. Brass was ideal for this purpose. It was relatively inexpensive, highly malleable and ductile, meaning it could be easily stamped and formed into the required cup-like shape, and it was resistant to corrosion. It also had an appealing golden sheen that complemented the painted wood of the pencil barrel. The manufacturing of the ferrule began with large sheets of brass of a specific thickness. A powerful stamping press, using a blanking die, would punch out thousands of flat, circular discs from the sheet. These discs were then subjected to a series of drawing operations. In this process, a punch would force the flat disc into a die cavity, causing the metal to flow and form a shallow cup. Several successive drawing stages, each with a slightly deeper die, were used to form the cup into a deep, cylindrical shape with one closed end, which would become the top of the ferrule. Once the basic shape was formed, the ferrule needed to be attached to the pencil. This is where the art and science of crimping comes into play. Crimping is a metal-forming process used to join two pieces of material by deforming one or both of them to hold the other. In the context of a pencil, the ferrule is crimped onto the wooden barrel. Early methods were often simple pressure fits, but these lacked reliability. The key innovation was the creation of a distinct, indented ring around the circumference of the ferrule. The earliest machines used a single ring crimp. The pencil, with the ferrule loosely placed over its end, would be inserted into a chuck. A set of hardened steel jaws or wheels would then press into the ferrule, creating a single, narrow groove that bit into the wood of the pencil, securing the ferrule in place. While an improvement, the single ring crimp could sometimes allow the ferrule to rock or pivot on this single point of contact. This led to the development and widespread adoption of the double ring crimp, which became a hallmark of American pencil manufacturing. This technique used two parallel crimping wheels to create two distinct indented rings, one near the top of the ferrule's skirt and one near the bottom. This provided a much more secure attachment, as the 2 points of contact prevented any wobbling or loosening of the ferrule. It was a simple, yet profoundly effective, mechanical improvement. After the ferrule was crimped to the pencil wood, the eraser plug had to be inserted and secured within the ferrule's cup. The most common method for this was known as clinching or staking. Inside the top portion of the ferrule, the stamping process would create small, sharp metal tabs, or prongs, pointing inward. The eraser plug was forced into the ferrule, and a final press operation would bend these small prongs inward, causing them to dig into the sides of the rubber plug. This mechanical grip held the eraser firmly in place, preventing it from being pulled out during use. The design of these clinching prongs was a closely guarded secret of each manufacturer, with different shapes and numbers of prongs being used to achieve the best possible grip. Thus, by 1900, the archetype of the modern pencil was firmly established. It consisted of a wooden barrel, typically cedar, containing a graphite core. This barrel was topped by a brass ferrule, secured with a double-ring crimp, which in turn held a pink, pumice-filled, vulcanized rubber eraser in place with an internal clinching system. This was the state of the art, a product of 30 years of gradual refinement in both chemical composition and mechanical assembly. The period from 1900 to 1940 can be characterized as an era of optimization and the introduction of new subtleties. The fundamental design remained unchanged, but manufacturers, facing stiff competition, sought to improve their products and lower their costs through small, iterative changes. In the realm of eraser composition, one of the most significant developments was the widespread use of an ingredient called Factice. Factice, also known as vulcanized vegetable oil, is a rubber-like material produced by heating vegetable oils, such as rapeseed oil or soybean oil, with sulfur. The resulting substance, which could be either a dark brown or a creamy white solid, was not a true synthetic rubber, but it served as a highly effective extender and processing aid when mixed into natural rubber compounds. Adding Factice to the eraser recipe had several benefits. First, it was significantly cheaper than natural rubber, allowing for a reduction in material costs. Second, it acted as a plasticizer, making the unvulcanized rubber compounds softer and easier to process in the mixing mills and extruders. This reduced the energy required for processing and could speed up production lines. Third, in the final vulcanized product, the presence of Factice resulted in a softer, smoother eraser that was less abrasive than the older, heavily pumice-laden formulas. It improved the feel of the eraser and its performance on smoother paper surfaces. The balance between pumice for abrasive power and Factice for softness became a key part of an eraser company's proprietary formula. This era also saw a greater emphasis on branding, which was often expressed through the ferrule. While the double-ring crimp remained the standard for securing the ferrule, companies began to use the ferrule itself as a visual differentiator. The Joseph Dixon Crucible Company's iconic Ticonderoga pencil, for example, introduced its signature green ferrule with a yellow band, a painted design that made it instantly recognizable. Other manufacturers might use different metals or platings, such as nickel plating over brass, to give their ferrules a silver appearance, distinguishing them from the common gold-colored brass. Knurling, a process that creates a textured, crisscross pattern on the surface of the metal, was also sometimes applied to the ferrule, ostensibly to provide a better grip, but also serving as a subtle aesthetic touch. The machinery used in pencil factories became increasingly sophisticated and automated. What was once a series of discrete, manually fed operations began to be integrated into continuous production lines. Machines were developed that could take a painted and finished pencil barrel, automatically fit a ferrule, perform the double-ring crimp, insert an eraser plug, and perform the final clinching operation in a seamless, high-speed sequence. The sounds of these factories were a rhythmic symphony of industry, the whir of motors, the stamp of the blanking presses, the clatter of pencils moving along conveyor belts, and the distinct, percussive chunk of the crimping machines, repeated thousands of times an hour. This period of steady, incremental refinement came to an abrupt and dramatic halt with the onset of the Second World War. The war was a catalyst for unprecedented technological change, and its impact on the humble pencil eraser was profound, driven by a global crisis in a critical raw material, natural rubber. In late 1941 and early 1942, the Japanese military campaigns swept through Southeast Asia, capturing Malaya, Singapore, and the Dutch East Indies. This region was the source of over 90% of the world's natural rubber supply, which had been cultivated there in vast plantations. With a single stroke, the Allied powers, including the United States, were cut off from their primary source of this vital strategic material. Rubber was essential for the war effort, needed for everything from vehicle tires and aircraft hoses to gas masks and battleship gaskets. The response from the United States government was swift and massive. The War Production Board immediately halted the use of crude rubber for all non-essential civilian goods, and the pencil eraser was certainly deemed non-essential. A nationwide campaign was launched to conserve rubber and to collect scrap rubber for recycling, but recycling alone could not meet the colossal demand. The only long-term solution was to create a domestic synthetic rubber industry from scratch, and to do so at an almost unbelievable speed. The US government established the Rubber Reserve Company and poured immense resources into a crash program involving a consortium of chemical companies, tire manufacturers, and universities. The primary focus was on a type of synthetic rubber known as GRS, which stood for Government Rubber Styrene. Today, it is more commonly known as SBR, or styrene butadiene rubber. The chemistry of SBR was fundamentally different from that of natural rubber. Natural rubber is a polymer of a single monomer. Isoprene, SBR, by contrast, is a copolymer, meaning it is made from two different monomers, styrene and butadiene. Both of these chemicals could be derived from petroleum, a resource the United States had in abundance. The process involved reacting these two liquid monomers in an emulsion, a soapy water solution, to form a milky synthetic latex, which could then be coagulated to form a solid synthetic rubber that mimicked many of the properties of natural rubber. For the pencil manufacturers, this was a moment of immense challenge and innovation. Their supply of natural rubber had vanished, and their existing formulas, carefully perfected over decades, were now useless. They had to learn how to work with this new synthetic material, GRS, which behaved differently in every stage of the manufacturing process. The SBR compounds required different types and amounts of additives. The vulcanization process, the crucial curing stage, had to be completely recalibrated. SBR required different curing temperatures, different pressures, and often different chemical accelerators to ensure the sulfur cross-linking occurred properly. The early batches of synthetic erasers were often of poor quality. Some were too hard and brittle, cracking with use, while others were too soft, leaving greasy smears on the paper. The chemists and engineers at companies like Eberhard Faber, Dixon, and the American Pencil Company worked tirelessly through trial and error to develop new formulas based on this unfamiliar polymer. They discovered that SBR had a higher abrasion resistance than natural rubber, which meant that the amount of pumice could be reduced. They found that it responded well to different types of plasticizing oils and fillers. The familiar reddish-pink color was maintained with iron oxide, providing a semblance of continuity for the consumer, but the chemical heart of the eraser was now entirely different, born not of a tropical tree, but of an oil refinery. The war also impacted the ferrule. Copper, and by extension brass, was a critical war material, used for shell casings, wiring, and other military components. Its use in civilian products was heavily restricted. Pencil manufacturers had to find alternatives. Many switched to using steel for their ferrules. Steel, however, is prone to rust, so these steel ferrules were often plated with another metal, such as nickel, zinc, or sometimes even a thin layer of brass, in a process known as brass washing, to provide corrosion resistance and a more familiar appearance. Some also experimented with aluminum, which was also a strategic material, but became more available as wartime aircraft production ramped up. This period saw a diversification of ferrule materials driven entirely by the necessities of a global conflict. By the end of the war in 1945, the American synthetic rubber industry was a behemoth, capable of producing nearly 1 million tons per year. The pencil industry had successfully navigated the transition, and the synthetic SBR-based eraser was now the new standard. The post-war period, from the late 1940s through the 1950s and 1960s, saw the cementing of SBR's dominance and the rise of an entirely new class of eraser material. When natural rubber from Southeast Asia became available again after the war, it failed to recapture its old market in the eraser industry. The SBR production infrastructure was already in place, its supply chain was domestic and stable, and its price was lower and less volatile than that of natural rubber. Manufacturers had perfected their SBR formulas and had no incentive to switch back. The SBR eraser compounds of the 1950s and 1960s became increasingly sophisticated. The science of polymer chemistry had advanced significantly during the war, and a wide array of new chemical additives became available. Instead of relying solely on factice or simple mineral oils as plasticizers, manufacturers could now use synthetic chemical plasticizers, such as phthalates. These compounds offered much more precise control over the final properties of the eraser, allowing chemists to fine-tune the flexibility, durometer, a measure of hardness, and erasing characteristics of the product with remarkable accuracy. The role of pumice as the primary abrasive also continued to diminish, as chemists learned how to control the properties of the rubber itself to achieve a clean erasure with less wear on the paper. However, the most significant innovation in eraser materials during the mid-20th century was the development of plastic or vinyl erasers. These erasers were not based on rubber, either natural or synthetic, but on a plastic polymer, most commonly polyvinyl chloride or PVC. The erasing mechanism of a PVC eraser was fundamentally different from that of a traditional rubber eraser. A rubber eraser, even the more advanced SBR formulas, still relied to a large degree on mechanical abrasion. It worked by rubbing away the paper fibers to remove the graphite. A PVC eraser, on the other hand, worked through a process of adhesion and transference. The PVC was heavily loaded with plasticizer chemicals. These plasticizers made the surface of the eraser slightly sticky at a microscopic level. When rubbed against a graphite mark, the graphite particles would preferentially adhere to the plasticizer-rich surface of the eraser, lifting cleanly from the paper. The used portion of the eraser would then slough off in small, stringy clumps, carrying the graphite away with it and exposing a fresh, clean erasing surface. This new technology offered several distinct advantages. First, because it did not rely on abrasion, it was exceptionally gentle on the paper surface, making it ideal for artists, draftsmen, and architects working on delicate papers. Second, it produced significantly less dust than a rubber eraser. Instead of a fine, gritty powder, it created cohesive strands that were easy to clean up. These new white vinyl erasers began to appear on the market, often sold as separate blocks, and they quickly gained a reputation for high performance, especially for technical drawing and artwork. While the traditional pink SBR eraser remained the standard on the end of the common yellow pencil, the advent of vinyl erasers marked the first major challenger to the dominance of rubber-based erasing technology in nearly a century. In the world of the ferrule, the post-war era was one of standardization and cost efficiency. The double ring crimp was now utterly ubiquitous, the unquestioned standard for quality pencil manufacturing. The major shift was in the material used. As aluminum production became more cost-effective after the war, it began to supplant brass as the ferrule material of choice for many mass-market pencils. Aluminum was lightweight, rust-proof, and significantly cheaper than brass. It had a silvery appearance that became just as common as the traditional gold color of brass. While premium pencils might still feature brass ferrules as a mark of quality, the everyday pencil in a school or office was increasingly likely to be capped with aluminum. The crimping and clinching processes themselves were refined to new levels of speed and precision. The machines that performed these tasks were masterpieces of mechanical automation, operating at incredible speeds. Let us take a moment to visualize this final stage of assembly in a mid-century pencil factory. A long line of painted pencil barrels, their ends precisely shaped, moves along a track. At the first station, a chute feeds aluminum ferrules, correctly oriented, one by one. A mechanical finger pushes a ferrule onto the end of each pencil. The pencil then moves to the crimping station, where two hardened steel wheels spin into place, pressing the twin grooves into the ferrule with a precisely calibrated pressure, locking it onto the wood. The pencil then proceeds to the next station, where a long extruded cord of pink SBR eraser material is being fed into a rotary cutter, which slices off a perfectly sized plug. A plunger mechanism takes this plug and inserts it into the open cup of the ferrule. Finally, the pencil moves to the clinching station. Here, a set of internal punches descends into the ferrule, pressing the small metal prongs inward to bite into the rubber plug, securing it permanently. This entire sequence, placing the ferrule, crimping it to the wood, inserting the eraser and clinching the eraser, would take less than a second for each pencil. Thousands upon thousands of pencils would flow off these assembly lines every hour, each one a tiny, perfect product of a century of accumulated chemical and mechanical knowledge. By 1970, the end of our period of study, the pencil eraser had reached a state of mature technological development. The standard American pencil featured an SBR-based eraser, its formula a complex blend of synthetic rubber, plasticizers, and perhaps a small amount of mild abrasive, colored pink, more by tradition than necessity. This eraser was held in an aluminum ferrule, attached with a crisp, efficient double-ring crimp, and secured by an internal clinching system. This object, so mundane and familiar, was the culmination of a slow, quiet journey. It was a journey that began with breadcrumbs and sticky, raw rubber. It was revolutionized by Charles Goodyear's accidental discovery in a Massachusetts kitchen. It was given its iconic form by Hyman Littman's patent and the anonymous mechanical engineers who designed the first ferrule crimping machines. It was standardized and mass-produced by the industrial giants of the Gilded Age, who perfected the formula of rubber, pumice, and sulfur. It was subtly refined in the early 20th century with the introduction of factice and the use of the ferrule for branding. It was fundamentally transformed by the global crisis of the Second World War, which severed supply lines and forced a complete transition from a natural, plant-based polymer to a synthetic, petroleum-based one. And finally, it was perfected in the post-war boom, with advanced chemistry and high-speed automation, even as new plastic-based technologies began to challenge its long-held reign. Each tiny pink tip on a yellow pencil is a silent monument to this history. Its material composition tells a story of global trade, agricultural science, and polymer chemistry. Its metal collar, with its two small indented rings, speaks to a history of metallurgy, mechanical engineering, and the relentless pursuit of manufacturing efficiency. It is a history without grand battles or famous speeches, a history written in the quiet language of chemical formulas, patent diagrams, and the rhythmic hum of factory machinery. It is the subtle, century-long evolution of a simple, perfect tool for making and for correcting our mark upon the world. And now, with the details of its composition and construction laid bare, perhaps you can rest, feeling the gentle weight of this small, simple, and surprisingly complex history.